There are two main directions how to prepare the estimation, and in these lectures we are going to examine the two cases. In the first case, the number of measured data is fixed. In this case, we have to prepare the model. Second, we have to do the measurement, and then we have to do the identification. And in this case, the identification can be done offline because we have got all the measured data. This offline estimation is called the batch processing mode. First of all, I repeat the quadratic function from the last video, and it is easy to see that the number n is given, it is fixed. So we have got some measured data, y index I, it is coming from the output of the process. The input of the process is collected in the row vector phi index I transpose, and the unknown parameters are collected in the vector p hat. We are going to do the difference of it. We have to take the square. We have to sum all the individual errors, and we have to take the half of it. Okay, this is the quadratic error function. But in the future, we are going to work with matrices and vectors because it's a much better way from the application, from the numerical application point of view. That's why we are going to introduce the following notations. So there is a vector, capital Y, where we are going to collect all the measured output data. So you can see that the first row is y index 1, the second is y index 2, and so on. The last is y index n, so it's a column vector with n rows and 1 columns. So in this vector we are going to collect all the measured output data. Second, there is a matrix, it is called phi, capital Phi, because in this matrix we are going to collect all the measured input data, phi 1 transpose, phi 2 transpose, etc., phi n transpose. So this matrix has n rows and let's say p columns if we have got p unknowns, and the parameter vector contains p parameter data and only 1 column. So these are known, and we have to calculate this vector element. So next we have to reformulate the quadratic function v, and we are going to prepare it in the next. So if we put all the y elements from here and all the phi's from here and all the p's from here into vectors and matrices, we can do the following: the half, the vector capital Y minus phi transpose, phi and p. We have to take the transpose of it, and next I copy it, because in this case we will have a row vector because of the transpose in the first, so this will be a row vector. The second will be a column vector, and if we multiply a row vector with a column vector, we are going to get a scalar value, and this will be the same as this one and the first one, but with vectors and matrices. And so for the future work, it's much better to work with a matrix formulation. So the next is to do the following. I am going to multiply this element with this element. In this case, I get y transpose y. So it's also a scalar value. Minus the first element from the first bracket with the second element from the second bracket. So it will be y transpose phi p hat. So the next is the second element from the first bracket and the first element from the second bracket. But we have to take care because phi p hat transpose, there is a rule for this. This is the same as p hat transpose phi transpose. So we have to take the transpose of the individual elements inside the bracket, and then we have to rotate them. Okay, we have to replace them. So that's why I am going to write the following: p transpose phi transpose and y, and finally plus the second element with the second element from the first and the second bracket, p transpose phi transpose phi and p hat. In the second step, we have to take care of these two elements because these two elements are the same. Why? I put this here. So y transpose phi and p hat. So I am collecting here the second element. This is a scalar value because this term is an element of the quadratic error function, and the quadratic error function is a scalar function. So this element is also scalar. We can take a look at according to the size of the matrices and the vectors. So I can take the transpose of it. The transpose will be p hat transpose phi transpose and y. So in this case, we also have to rotate the three elements. So p, the last one, will be the first one, phi will be the second, and y will be the last one. And we have to take the transpose of the elements individually. Okay, the third element I just copy from the last line, and y. So we can see that these two elements are exactly the same, and it's a very good news for us. I copy the first element, I take the half of it, plus p transpose phi transpose phi and p hat. So these two elements are exactly the same. I put a line here because on the left I just put some remarks if someone don't know this. So the next is the half y transpose y minus 2 p transpose phi transpose and y plus p hat transpose phi transpose phi and p hat. Let's have a closer look at this result. The last element, this one, contains two p's. It means p square. This is the second order term of this quadratic function, This is why we call it quadratic, because the p has a quadratic formulation. The second element, this one, contains only one p. It means this is the linear element of p, and the first term does not contain any p. So if we take the derivative of v according to p hat, we have to get 0. Because in this case, this quadratic function has minimum. So we have to take the derivative and we have to make it equal with 0 vector, of course. And in this case, we are going to get the following. The first element containing y transpose y is, we can forget it. The second will be minus phi transpose and y. And finally, the last one, it contains p square, and if we take the derivative according to p, it will contain 2p, and then this half is going to eliminate this term. That's why I can write phi transpose phi p hat. This is the derivation rule according to p vector, p hat vector. So I can write two algebraically equivalent form. The first form will be the following. I just reformulate the last equation. Phi transpose phi and p hat is equal to phi transpose and y. If we have a closer look at the phi transpose and phi contains known elements from the input measured data. The vector y contains known elements from the measured output data. The only one unknown is the p hat vector. So we can write the following. P hat is equal to phi transpose phi inverse phi transpose and y. So this is a solution of this equation, and we can get the parameter vector elements. So sometimes this inverse is very difficult to take because it is depending on the measurements. So sometimes it's difficult numerically to calculate by a software the inverse matrix. So this is why sometimes it's much better to use the so-called normal equation. This is the normal equation. Because for the solution of normal equation has a larger palette of functions and techniques, and I put some of them to here, which can be found in the typical software. The first is SVD. This is called the singular value decomposition of the matrix phi transpose phi. The second is, for example, the Cholesky factorization, and there is the well-known Moore-Penrose pseudo-inverse, which can be done by many software tools that can be found in the works. So there are, okay, one note here too, because this is the first, this is the second. These are algebraically equivalent, but in many cases it's much better to use the first one, the normal equation, because there are more possibility to solve it. The inverse is sometimes difficult, numerically difficult to solve.